Mr. Ransberg again, and I am back to finish up the binomial portion for lesson 6.3. As you can see highlighted over to the side there is we are going to focus on the third learning objective in this video. One of the main things we're going to do is we're going to focus on approximating normality using a binomial distribution, which is very weird to say, but we can do it. So we're going to pick up in your notes packet at slide 14. We ended at slide 13 in the previous video. And when we're looking at the mean and standard deviation of a binomial distribution, so let's kind of refresh our memory a little bit on random variables. Everything always goes back to the idea of shape, center, and spread. And I want you to keep that in mind, is shape, center, and spread. And so if we have a random variable that, let's just say x equals, because if you don't define it, you don't get to use it. So if x equals the number of children with type O blood in a family of 5 children, so we're on that example again, we have a random variable. We can see the probability distribution in a table there, and we can also see it in a graph off to the side. And you look at that, if you look at the shape, the center, and spread of that, the shape looks like it is slightly right skewed. And so the probability distribution of x, we get to use it because we defined it, is skewed to the right. And what does that mean? It's more likely that we have 0, 1, or 2 children with type O blood compared to 4 or 5 on it, because most of the data is over on that left side of the graph. The center, if I look at the median in this situation, the median of this is going to be 1. If I would use the mean, we have that formula for a random variable. We can take all of our values for that random variable. We have 0 children with type O blood. We can multiply by its corresponding probability. We have 1 child with type O blood. We can multiply by its corresponding probability, and then dot, 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 and do the last one, that good old dot, dot, dot. And that's going to give us a mean for that random variable, mu sub x equals 1.25. And we can do that same process. This is for random variables. This is covered in the first video, remember, for standard deviation. We can take the distance of 0 from that mean and square it. Then multiply by its corresponding probability. We can do it for the second term. The distance of 1 from 1.25. Square it. And multiply by its corresponding probability. And of course, dot, 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 gotta love it, the last one. 5 minus 1.25 squared, and multiply by its corresponding probability. Now, you could type all of that in your calculator. Or, remember, I went through this in the video, and I know Mr. Ray Nichols went through this in the video. You can go to Stat, Edit, and type in your values for the random variable in your L1, type in their corresponding probability in their L2. And that's what I have here done. And I can go to Stat, Calculate, 1 variable statistics, 1 bar stats. Your L1 is your list. The frequency list is your probability. Remember, we used to do these in chapter 3, and this was blank. So you have to be able to remember that when you're dealing with probability distributions, the probability part of the distribution goes in your L2, and that's your frequency list, and go to calculate. And that's going to give me the same mean and the same standard deviation. Now, for the work, I would do that whole dot, dot, dot. For the values, I would use my calculator like I have up above, and that's going to give my answer. So I would show this, but I would use the calculator list to get that one. So that's my variance, and I'm going to square root that and get my 0.968, and you see that up in the calculator for it. Sorry about that. So when we go through, there it is. That's a refresher of random variables. So how does this relate to binomial distributions? Well, it's interesting, because if we were to take a look at it, the mean is 1.25. Mu sub x is 1.25. Could I have done this another way? And it's very interesting that we knew from before in the previous prompt in the notes, previous video, that there was a 0.25 chance that a child would inherit the type O blood. And if I were to take that 5 and multiply by 0.25, I would get 1.25. Mind blown. For a binomial distribution, so you had the random variable, that was the stuff in the previous slide. For a binomial, to calculate its mean, we can just take our sample size and multiply by the probability of success, and we're done. That gives you your mean. So yes, I could do all of that, and the dot, dot, dot stuff. Or if I can tell it's a binomial probability situation, I can just use mu sub x equals n times p. Now, it probably is not obvious for the standard deviation formula, and that's okay. But for the standard deviation, it's going to be the square root of your sample size times p, which is the probability of success, times 1 minus p, which is the probability of failure. So it's really the square root of your sample size times the probability of success times the probability of failure. That is your standard deviation. These formulas only work for your binomial distributions. They do not work for any others. And that's kind of why we started with the problem the way we did in this video is I'd have to analyze it to determine it's a binomial. If I didn't, I'd have to do the random variable approach. But if I knew it was binomial, I can just go ahead and use this formula. So here we go. This is the stuff we kind of looked at before. Since it's a binomial, random variable, and I know we could cross this out. It's not a probability of 1/3, it's a probability of 1/4, and I'll write it as 0.25. I can use these formulas now. So mu sub x is going to be my sample size, which is 5 times 0.25. That's what gave us the 1.25 for our mu sub x. Now, how do I interpret it? I interpret it by saying in the long run. Always a good way to interpret your means that way. In the long run, you would expect about 1.25 out of 5 children to have type O blood. So notice, it's not just saying you'd expect 1.25 children. 1.25 out of 5, because that was our sample size. Now, when we're dealing with our standard deviation, you would have the square root of 5 times 0.25 is your probability of success, which means your probability of failure is 0.75. Here's how this one works. On average, we'd expect the number of children out of a family of 5 to vary by, and remember, it's an approximation, so I'm going to say by about 0.968 children from the mean, the average distance from the mean of 1.25 children. So that is our interpretation of mean and our interpretation of standard deviation of a binomial. It's easy enough to remember, but it is on your formula sheet. And so we have these shortcuts right over there to help us define the mean and the standard deviation of a binomial distribution. It's rather than doing the random variable approach that we just did at the beginning of this video with that whole dot 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 thing, we can use these shortcuts to help us with the mean and standard deviation, which is awesome. And so you have to be asking right now, okay, Mr. Ainsberg, there's got to be a catch. So what's the catch? And you're right, there is a catch. These formulas are great. And the reason why we're able to do these is because the previous problem was independent. And because it was independent, the blood type of one child is not going to affect the blood type of another child, we were able to use these shortcuts, which is great. But what if it's not independent? And that's where this part comes in. So there is a catch. That was a good question. The catch is this. If it's not independent, it's kind of like sampling without replacement. So let's use that as an example. Is if I am trying to figure out the proportion of New Albany High School students that have blonde hair. If I decide to randomly select a student, of course we're going to do it randomly, because who wouldn't do it randomly, and determine if they have blonde hair. And I do one student from the population. So I randomly select. Now, yep, blonde hair. Now, what if I do that to 2 students? Well, if I do that for 2 students, I'm going to look at one student. Yep, blonde hair. Look at the second student. Nope. Well, when I take the one student, I'm really removing them from the population. I'm not going to go back and look at one student, go sample one and go, hey, nope, you don't have blonde hair, and then pick that same student again to determine if they have blonde hair. Once you use that student, whether it's 2, 3, 4, whatever the sample size is from the population, you're not going to put them back in and select from them again. So how many is too many for a sample? And that's the question for independence we're looking at, is how many can I take before I start influencing the result from before? And what we do is we use something called the 10% condition. You can see that over to the side on the screen. And that's telling you that, hey, if I have 10 times my sample size, that has to be smaller than my population. At least, 1/10 of the population, your sample size must be smaller than that. So I'm telling you this now, but let's see it work out mathematically here. So if I'm looking at 10% of CDs have defective copy protection schemes that can harm computers, and a music distributor inspects a simple random sample of 10 CDs from a shipment of 10,000. So there's 10,000 CDs. and they are inspecting a simple random sample of 10. So the real probability of this situation is following that 10% rate, I would have out of the 10,000 CDs, 9,000 of them would not have a defect. No defect. If 10% is a defect, 90% is not. 90% of 10,000, 9,000. So as soon as I pick that one CD, and let's say there's no defect on it, now there's 9,999 CDs in that shipment. So now the probability changes. I have 8,999 out of that. 8,998 out of that. So as I keep drawing CDs, I'm now changing the total in that shipment. I'm influencing it. It's not independent. And my probability is 0.3485. However, if I treat it as independent, and that's what that next line shows you, and I treat it like a binomial still, I would get 0.3487. So if I'm using that, I'm assuming it's independent, but it's not. But notice that difference is not very much. 0.3485 and 0.3487 is so small of a difference between them. So as long as we don't sample more than 10% of the population, which is what this part of the formula means, as long as I don't sample more than 10% of the population, I can do sampling without replacement. I can ignore the fact that they're not independent. In other words, and this is, by the way Mr. McNichols and I like to do it, is the population must be bigger than 10 times your sample size. That's a quick way to figure it out so you don't have to do the 10% idea. So this is called the 10% condition. We're going to use it a lot in the future. And one thing I didn't quite say yet, you know I'm not going to miss out on my opportunity, is you better define your population. If you don't define it, you don't get to use it. And so, you better define your population. So here is from the textbook. When the population is much larger than the sample, a count of successes in a simple random sample of size n has an approximately the binomial distribution with n equal to the sample size and p equal to the proportion of successes in the population. That's the textbook. Here's Mr. McNichols. In other words, sometimes a situation may not be strictly independent, but close enough for practical purposes if the population is much larger than the sample. I think I need to work on my impression of Mr. McNichols. But in other words, is, hey, you know what, the situation is not independent, but it's close enough for us to ignore because our population is so much larger than our sample, 10% condition. So let's try it out. So that tells us, and I want you to realize, this right here is the idea of independence. In order for us to use the binomial distribution, that shortcut, we need independence. And if it's not independent, then we need to make sure that we have a large enough population that it's not influenced by the sample. The next part, so I'm going to draw a line. The next part is, well, how do we deal with normality? So as our sample size increases, we can see from these pictures here that our distribution is going to start to get approximately normal. So that's interesting. If I have a sample size of 10, we can see that graph is slightly skewed to the left. As I went up to 20, you know what? That isn't as bad. Its shape changed a little bit. It still doesn't look approximately normal, but it's interesting that it got closer to it. Now, when I went to 50 for my sample size, wow, like that is an approximately normal distribution. That looks, mound-shaped, looks symmetrical on it. And so here's how this works. So, independence. Can I use my shortcuts? I can use my shortcuts if I'm sampling with replacement or if I'm sampling without replacement and that 10% condition works. Perfect. Can I use normality? That's the second question we're addressing. You can use normality if you have at least 10 successes and 10 failures. And that's that box over to the side. Is if I have at least 10 successes and 10 failures, I can approximate normality. And that is what this is telling you. That, in words, is at least 10 successes and 10 failures for it. So then we can do approximate normality. So when we're going through this, we can use our probability of success times our sample size has to be larger than 10. Our probability of failure times our sample size has to be larger than 10. At least 10 successes and 10 failures, then you can approximate normality. So here's what this means. if you have a binomial distribution, which is what this is telling you right here, if I have a binomial distribution and I have enough trials so that I have at least 10 successes and 10 failures, I can use normal approximation for it. So that's something to keep in mind. And if I can use normal, I can use table A. I can use z-scores. I can go through this. So it's really interesting that that can happen. Now let's put it all together. So a sample survey shows that fewer people enjoy shopping than in the past. A survey asked a nationwide random sample, because who wouldn't do a random sample, of 2,500 adults if they agreed or disagreed with the statement, I like buying new clothes, but shopping is often frustrating and time-consuming. Suppose that exactly 60% of all adult U.S. residents agree with this, if asked the same question. Let X equals, again, not going to miss my chance, if you don't define it, you don't get to use it. Estimate the probability that 15, 20, or more of the sample agree. So here we go, everything all at one time. Verify that X is approximately a binomial random variable. So what does this mean? If we want to determine that this is a binomial setting, you know what we better do? We better check the bins. So, is it binary? Well, yes. People either agree or they disagree. So I'm going to define, and this is what you have to deal with. You have to state success equals agree, failure equals don't agree, disagree. So you need to state those. What are the two binary outcomes? Success is agree, failure is don't agree. Is it independent? Well, we're sampling without replacement. I mean, I'm not going to ask an adult how they feel about shopping and then go ask that same adult how they feel about shopping. That's not right. If I ask somebody already, I don't want to use them a second time in this sample. So we're sampling without replacement. So, oh no, that's not independent. But good news. Because it's out without replacement, I can check my 10% condition. Is my sample size, if I take 10 times my sample size, is that smaller than my population? I used a capital N there. I have yet to even state what capital N is. I better, if I want to use it, I better define it. My capital N is my population. My population in this case is all U.S. adult residents. Now that I defined it, I can use it. So 10 times my sample size, 10 times 2,500, so 25,000 less than or equal to N. All right, so if I go through this, does this work? Is there more than 25,000 U.S. adults? Yes. Yes, there are. But I can't just go, yes, there are, and then leave that and then go on to the next step. I better state that. It is safe to assume there is more than 25,000 adults in the U.S. You better state it. And I know I keep saying if you don't define it, you don't get to use it. And it's the same here. Congrats, you did the 10% condition, but state the 10% condition. State what that means. Hey, I'm sampling without replacement. And that's when you look at our writing. You would be writing all of this down on a free response problem. That's your job. We're trying to show you the right way to word it. So since we're sampling without replacement, I'm going to state that. I better check my 10% condition. Good news. It's safe to assume there's more than 25,000 U.S. adults. Therefore, I can ignore the fact that it's not independent and I can continue on with this situation. So I have N. Is my sample, so is there a fixed number of samples? Yes, there are. There's 2,500 trials. So there's a fixed N. And then finally, is there a fixed probability of success? Yes, we were told 60%. So good news is, verify that I can do a binomial random variable, check the bins, and I did. It was a little nerve-wracking there for that independent. I was a little cautious because it's not independent because I'm sampling without replacement, but 10% condition saved us. Now, we are going to check the conditions for using a normal approximation. So, independence, 10% condition. Conditions for a normal approximation. In order to take this, in order to take an n comma p for a binomial distribution and say it's going to be normal, we have to use this and this. But in order for that to happen, I must have at least 10 successes and 10 failures. So I have to take n times p, and that better be bigger than 10. So my sample size was what, 2,500? And my probability of success is 60%. So is that larger than 10? Is 60% of 2,500 larger than 10? Good news, yes it is. 1,500 is larger than 10. That's successes. Now I want to look at failures. So successes, good. Failures, do I have at least 10 failures? So n times 1 minus p. Is there at least 10 failures here? And if I do 2,500 and I'm multiplying by, well, probably a failure then would be 40%. And in that case, I get 1,000. And so I have more than 10 failures. Perfect. You know what? We can do this, but I better state that. I can't just make that my final answer. If I'm checking the conditions, I better say I can do it. So, since there is at least 10 successes and 10 failures, we can approximate normality. It's that whole idea of you better state it. Yes, congratulations, you showed there was 10 successes and 10 failures. But what does that mean? It means you can approximate normality. Now calculate the mean and standard deviation. So now I'm able to do this, which is great. So the mean says take your n times your p, which is 2,500 times 0.60, which is 1,500. For your standard deviation, take the square root of your n times your probability of success times your probability of failure. And when I'm looking at that, I'm going to take the square root of 2,500 times 0.6 times 0.4. And in that case, when I'm looking at it, that's going to be about 24.49. And so I'll write it a little bit nicer. Sorry, my handwriting's getting worse. About 24.49. So now I know this. I know I have a normal. We did that on number 2. I know the mean is 1,500, and I know the standard deviation is approximately 24.49. So 2 and 3 allowed me to do this. I can now, if I know it's normal, and I know my mean, I know my standard deviation, I can go ahead and calculate it like I normally would. So here we go. It's going to take some time. There we are. All right, so if I put 3 and 4 together, here's what we know. We know this is our normal approximation, a mean of 1,500 and a standard deviation of 24.49. That is what we can see up here. That's what we found. Because I have that, I can then move on and say I want to find the probability of more than 1,520. Agree with it. So in that case, that's my observation. Observed minus expected over standard deviation. So my expected is my mean at 1,500. I can find my z-score. And so because I can do this, I can use the table A now, because I'm saying it's approximately normal. And that's where you can look at the work and see what I did. Now in this case, I have table A. Because remember, table A gives you area to the left, and you need to do 1 minus table A to get area to the right. The way I like to do it is I like to state the mean and the standard deviation, and then I like to label it. They're using the table here so you can see it there for it, using that distribution, and then you go from there. Now, if you wanted to use your calculator, you would do normal, CDF, lower bound. Well, if I want to use my z-scores, I could say my lower bound is 0.82, because this, by the way, and I would always label this is 1,520. That's a z-score of 0.82. Upper z-score, I could do 99. For a standard normal curve, that's a 0 and a 1. That's going to give me the same answer, 0.2061. I could also do normal CDF, lower bound 1520, upper bound 99 and 9999. My mean, which what do we say, 1500, and my standard deviation of 24.49. That's another way to do it in your calculator. Lower bound, comma, upper bound, comma, mean, comma, standard deviation. All right, there we go. So now let's do one last one. We can do it. Premature babies are those born more than 3 weeks early. Newsweek reported that 10% of the live births in the U.S. are premature. Suppose that 250 live births are randomly selected. Find the probability that the number of preemies is less than 20. So this is a state, plan, do, conclude. So state what is the probability that the number of premature babies is less than 20. So when we're planning, what we want to do is this. Did they do it right? Did they randomly select? Yes. The prompt states randomly selected. You always want to make sure, did they at least collect the sample right, which we know random selection is important when doing the sample. Is it approximately normal? I'm going to pause on that one and go down to the bottom one. I think the normality I'm going to save for the end. Since we're sampling without replacement, can we consider this sample independent? And that's really important. We're sampling without replacement. When a baby's born, they're born. They're not going to be born again. They're born. So since there's no replacement, I'm going to state that. Since we're sampling without replacement, I'm writing that down. I'm going to check the 10% condition, which means my population must be larger than 10 times my sample size. Well, look at that. I used a capital N there. I better define capital N. So capital N is my population. If I read the prompt, it says that we have premature babies are those born more than 3 weeks early. Newsweek reported that 10% of live births in the U.S. are premature. So 10% of live births in the U.S. are premature. So my population has to be all the live births in the U.S. So since I used capital N, I better define it. If you don't define it, you don't get to use it. And so I have 10 times my sample size. So 10 times 2,500. That is 10 times 250, which is 2,500. And is it safe to assume? Is it safe to assume there's more than 2,500 live births in the United States? And we'll say, yes, there is. So it is safe to assume there is more than 2,500 live births in the U.S. Now I can, since we're sampling without replacement, I know that perfect. The reason why I said pause and normality is in order to do normality, we have to do this. So I like to figure out, is it random? Is it independent? And then deal with normality. So normality in this case, I don't know. It's a binomial situation. So for normality, I better check, is there at least 10 successes and 10 failures? So let's find out. Probability is 10%, so I have 250, I was right the first time, times 0.10, I get 25. So in this case, I have at least 10 successes. Good. Failures, 250 times 0.90. And in this case, you get 225. I do have at least 10 failures. Do I stop there? No. I make the statement, since we have at least 10 successes and 10 failures, we can approximate normality. So I state it, and now I get to do it. I have, in this case, a normal distribution. Whoops. What's my center? Well, I need to do mu of x equals n times p. So 250 times 0.10. My center is 25. Well, what's my spread? My spread is going to be the square root of n times p times 1 minus p. So my spread is going to be the square root of 250 times 0.10 times 0.90. In that case, I get 4.74. So I have a standard deviation of 4.74. So once I define normality, I can go here. So I like to go random sample, independence, and then normality. Because once I do normality, I can state my shape, my center, my spread, and I now can label my normal distribution curve there. Magic. So, labeled. Now, what are we trying to figure out? In this problem, it says, what is the probability that the number of premiers is less than 20? So, I am trying to find out the probability that the number of premiers is less than 20. Alright, so I'm going to find my z-score. So 20 would be about right here. So there's where 20 is. And I want less than. So look at that. I am shading it. I'm good. That z-score looks like it's a little bit less than -1. So let's make sure. Z equals 20 minus 25. So it is negative there over 4.74. And I get a z-score of -1.05. So I have the probability that my z-score is less than -1.05. In this case, I can go to table A, and I can type it in to my calculator. You choose. I like to use the calculator. Normal CDF. And in this case, I have a left bound. Well, that goes to the left forever. So I'm going to do -99 because I'm going to use my z-scores. And my upper bound, my z-score was a -1.05. If I'm dealing with the standard normal curve, my mean is 0, my standard deviation is 1. So there I am, I get my answer, and I get 0.1468. So 0.1468 is my probability. I could also have done with my second var's original information once I find my z-scores. I could do my lower bound, again, I could say -99, I mean, looking at that, I could keep adding some 9s, it makes you feel better. And I could do my upper bound, it stops at 20. My mean was 25. My standard deviation was 4.74. Paste it. There you go. It's close enough on it. So that's our answer. And I think it's because I typed something in wrong maybe. Maybe I should add a couple more 9s. And so in this case, what does that mean? We need to conclude, what does that 14.68% mean? And so right here I have the original questions. Find the probability that the number of preemies is less than 20. Our statement was, what is the probability that the number of preemies is less than 20? So we have to answer that, but I have to answer that in context. And so here's the context. We defined N as all live births in the United States. And we based it off of a sample of 250. So it's always important to keep in mind what's your population, what's your sample, and what did you find in the do step. And so here is what this means. There is about a 14.68% chance that the number of U.S. premature births in a sample of 250 is less than 20. And so we can look at that and go, boom, we're done. That conclusion right there states what's our probability, the context of it. It states what's your population and what is the sample, because everything is based off that sample. And I think that's really important that you understand. And that's where this part came into play. The reason why I have to state my sample size in the conclusion is because the shape changes based off of the sample size on it. It does become approximately normal, but notice, this one didn't look too bad, but that is a completely different graph than the other one where there's 50. So in your conclusion, be sure you address, you know what is my population? What is the sample? Because your percentage is found from that sample on it. So we are done. You can see right there, geometric is next, and that will be by Mr. Nichols.